Coming to ATPZ, what it does, it can generate the test patterns. It can find redundant circuit logic. It can prove one implementation matches another. Okay. So these are some of the functions. Basically, what it's trying to do is it can analyze the design, means the netlist what you have given, and it will be able to say that what are all the faults in the netlist or in a given design are testable or untestable. Okay, and it can generate the test patterns for all that logic which can be testable, and it cannot generate the patterns for the logic which is untestable, and it will tell you that what are the untestable logics and why. Now you have a choice of live with that coverage, or you can go back and modify that untestable logic to make it testable. How? By inserting a test points, increase the controllability and observability, make it controllable and observable, and then push this untestable logic into testable logic. Okay, so all this kind of analysis and inputs, ATPG tool can do it for you. Why is the ATPG necessary? We already talked about it. We cannot go or afford to go by a functional way of testing, which is impractical. Then you need to go by a structural way of testing, and structural way of testing is the one which is supported by ATPG. Designer generated functional patterns typically provide only this much coverage, and even for this much coverage, you need to spend a lot of test time. It doesn't mean that you will never rely on the functional coverage, functional test patterns. There is a possibility. ATPG usually goes all the way to 98%, and 98, 99, 99.5 kind of things. And the top-up coverage of could be a 2%, 1%, or 0.5%. You can rely on the functional patterns to fill the gap and try to make it as a 100%. Okay, that's how the combination of ATPG plus functional patterns goes together. Some liner came up here that it can find the redundant logic, and somebody might have a question that what is the redundant logic. So to give you a quick understanding of what do you mean by redundant logic, I have added this slide. The redundant fault clause includes faults that test generator considered as undetectable. Okay, so as I said, testable, untestable, right? So by default, the tool will say that I cannot test it. What is that? Let's try and understand. Suppose you want to test a stuck at one fault on this node. We all know that by now. What do we need to do to test the stuck at one fault here? So you should be able to apply an opposite value, which is 0, to test this node, right? Remember that we already talked about AND gate, OR gate. How do we test it? So you want to apply a 0 to test the stuck at 1. Because when do you say that this node is stuck at 1 or not stuck at 1? If you apply a 1, you don't know, because the one what you have applied, it is propagating, or is it because the node is stuck at 1, it is propagating, right? Suppose if you apply 1 here, what value you expect here? Let's see, 1 came here. Is this because you don't have a stuck at fault and the one what you have applied came here? Or no, there is a stuck at fault here because of that 1 came here. Means if you apply a 0, also you will get a 1 because there is a fault. If there is no fault, if you apply a 0, it will get a 0. So how do you know that? Only if you apply opposite value, then you will come to know that, yes, is it? If you apply suppose a 0, what will happen? If there is no fault, 0 will come. If there is a fault, 1 will come, because the 0 is getting altered here as a 1 because of this stuck at 1. So you can enable the testing of a stuck at fault only if you apply an opposite value to what you want to test. So you want to test a stuck at 1, so obviously you need to apply a stuck at 0 value here. Good. What next? You want to propagate this input transition or this input value to output, right? You don't want the effect of this coming and affecting the value because this is what you are interested, this leg. So for AND gate or NAND gate, to make it transparent, you will apply a 1 here. So 1 will come here. Then whatever with the value here goes output here. If there is no fault, 0. If there is a fault, 1. Right? The same way it is inverted here. If there is no fault, it will become a 1. If there is a fault, it will become a 0. Fine. Now you want to take this value to the output because you need to observe the value at an output. You cannot observe the internal nodes. Output means this could be output, primary output port, or going to a scan flow, which is nothing but your virtual output. Right? Anything could be possible. So again, to make this AND gate transparent so that the value comes here will come to output, you need to make it 1 here. And to make this 1, you need to apply a 1 here. But the moment you apply a 1 here, you lose this testability. Because if you apply 1, you don't know whether you are getting a 1 because you applied or stuck at 1. Basically, the activating the fault we discussed, like we need to apply a opposite value. But to propagate this fault, you need a 1 here. So this is a deadlock, right? These are the faults, what you call it as a redundant faults. This fault cannot be tested because of the redundancy. And now, this fault cannot be tested, we understood that. But first of all, do we need this fault? Do we need the logic need to be implemented like this? That's the question. What this functionally, this logic is doing, A, B, and output is giving as a bar B. What it is doing, A, B. And so this functionality is something like A, B. And here it is coming as a B bar. Correct? And A, B bar, and this is coming as a B. So AB bar into B, right? What will happen? AB bar into B is A bar B plus again B bar B. B bar B is 0, right? B bar B is 0. So your final function is A bar B. De Morgan laws, if you remember. So why do I need such kind of logic to implement the A bar B? I'll simplify and try to do in this way. A bar, and this is B, and this is a integration function. So I got A bar B here. Why do I need to implement? The same functionality can be implemented like this and can be implemented like this. But if you implement like this, there are how many nodes coming here? See that how you are complicating a logic. When I say you mean say the synthesis. It has created one node. You know that each node will be having a stuck at 1, 0 and stuck at 0 probabilities. This is another node. 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 So you have 1, 2, 3, 4, 5, 6. There are 6 into 2, 12 faults possible in the circuit. Here 1, 2, 3, and 4. There are 4 into 2, 8 faults possible in this circuit. So the same functionality of A bar B can be implemented this way, which is a less number of faults and there are no redundant faults. So this explains the synthesis tool should be intelligent enough or should do a good job in terms of optimizing the circuits for a particular functionality. If it is implemented, your RTL into a first example or first model, then you will be having a more faults, which is not a DFT friendly. You will end up having a redundant faults, which will reduce the coverage and increase the gate count as well, by the way. Because the area of one AND and one NAND is more than area of one inverter and one AND gate. Okay, so area is not good, DFT wise it is not good, and of course the propagation delays are also higher. So this is not a good implementation by the synthesis tool. Okay, so this is what an example of a redundant fault. Now also one more thing you learned from here is, we know that already, a lesser number of faults, less number of patterns, less number of patterns, less number of test time, less number of test time, less number of test cost, or reduce the test cost. Okay. Now, how the silicon testing looks like. So you have an ATE. Once you as a DFT engineer generated the pattern using an ATPG tool, we already talked about, you simulate it and hand over the patterns to tester. And test engineer will convert those patterns into a compatible test format. And once silicon came back after manufacturing, they'll apply the patterns and they will read back the responses from the scanouts. And the pattern is a combination of two fields. I already told. Expected field and applied or input field. Right? Each pattern will be having this value. If apply this combination and I expect this to come, this is a pattern 1. So every pattern will be having these kind of structure. When you apply this at a scan inputs, you expect these at a scan outputs. That's what one pattern. Like this, you might be having thousands and millions of patterns. So what ATE will take this? It will take, this is the pattern what I need to apply, 0101, which is nothing but this. And what is expected? I expect when I apply this, I need to get 1110. This is the expected pattern. So it will apply this pattern here, complete the operation. It will read actual pattern. If the pattern coming up from the scanouts are exactly 1110, excellent. So what is expected and what is came back from silicon is matching. This pattern is passed. So pattern 1 is passed. Suppose instead of getting a 1110, we got all ones, right? Which is a mismatch. So there is a bit mismatch. That means now it says that pattern 1 is fail. Like this, it will continue testing all the patterns, thousands, hundreds, thousands, lakhs, whatever the number of patterns. And it will say that these are the end of the test, these are the number of patterns, and this is the pattern number failed, or all passing, like that. That's how the testing happens. Applies the input stimuli from the tester, measure the responses from the silicon, and if any pattern fails, it will try to escalate it if all are passing, which is good. Now, if you look at it, a bigger picture of an SOC, how it looks like and what kind of different DFT structures we have. If you remember in the first class, we talked about how we can divide the entire chip or SOC into multiple major components, which are analog, digital, memories, and IOs, right? So what we want to have the test methodologies or test processes to test each type of these structures, right? We don't want to use the same medicine for different diseases, right? So we want to have which technology or which methodology works for what testing, what logic testing. If it is a digital, maybe a scan is the best, or logic based is the best. For a memory, the memory based may be a best. For IOs and the board testing, the boundary scan may be a best, right? Like that. So if you see, this picture will give you an overview. Like if I have memories, I have a memory based to test. If I have the digital logic, the internal scan chain structure is the best. And maybe I can use the logic bits for some of the existing scan chains, and I will use the boundary scan for IOs. So like that, we have a different test structures and the test logic shown to test the different structures. So these are the boundary scan cells which are already inserted here. You can see that connected to the boundary scan logic. So basically, pads and IOs both are together, memories and log blocks and logic scan chains. These are comes under a digital, and this is a boundary scan which we are adding as a